Okay. So everybody, welcome to the 124th MedAI Group Extend sessions. Today we have with us Rahul Thapa, who is a second-year PhD student at Stanford University, and he's working under the guidance of Dr. James Zhu. And his my primary focus is on AI in medicine. Today he'll be talking about his work on SleepFM, which is a multimodal representation learning for sleep across brain activity, ECG, and respiratory signals. Currently, he is also a research intern at Together AI, where he concentrates on multimodal models. Rahul's research interests lie in the development and application of multimodal models, and he has experience working with sleep signal data and biomedical image, text, and video data. So before we start, Rahul, how would you like to take questions? Do you want to take questions while you are giving the talk, or you want to keep the questions for the end of the presentation?
Yeah, I usually prefer during the presentation because a lot of times you forget things at the end. So yeah, feel free to stop me, and I'll also have like pauses in between asking for questions.
Okay. Thank you so much, Rahul. And with that, without further ado, we will start the presentation, and over to you, Rahul.
Thank you. Thank you for the nice intro. Um, my name is Rahul Thapa, and like she said, I'm a second-year PhD student at Stanford. And today I'll be talking to you about one of the projects that I've been working on called SleepFM, where the FM stands for foundation model, not frequency modulation. This project was basically started about a year ago, maybe like 8 months ago, as I was doing my rotation project at Stanford during my first year. So generally, the motivation behind this was I was really interested in multimodal models, and my PI, James, had also collaboration with the sleep clinic at Stanford. So we were brainstorming what we can do with the data, and that's how the project came about. And I'll go into more details about exactly why we did it and what was our exact motivation. But yeah, that's like the gist of it. Okay, so let me get started. Oops. So the agenda for today is as such. I'll quickly start with the motivation. I'll walk you through some of the data that we have, how it looks like, and the modeling approach we use, and some results. And I'll like to end with some limitation of the work and the work that I've been doing as a follow-up to this. This work was actually published at ICML, so it's like a few months old now, and we have some interesting follow-up work as well that I can briefly talk about. Okay, so let's go over the motivation. So we all know how it feels like when we have an all-nighter, right? We may feel energetic initially, but eventually as the day goes by, we just feel like really bad. And we also know when we get really good sleep, we feel very energetic and motivated to do anything and everything. That's the amount of time we sleep. 33% of our life is spent on sleeping on average for an average person. This just leads us to think that there must be something interesting going on in sleep, that by evolution and by nature, we spend so much time sleeping. And some of the things that sleep does, as the study shows, are mood regulation, information processing, memorization, physical restoration, and whatnot. And there are a bunch of sleep disorders like apneas and sleep paralysis that could really impact your sleep and quality of life. And this is further supported by multiple studies showing association between sleep and neurodegenerative diseases, cardiovascular diseases, obstructive apneas, and comorbidities like that. So this is also further, the motivation is further also because of the data we have at hand. A lot of the sleep data actually comes from the structured sleep clinic. Just at Stanford, we had about 30 to 40,000 of this sleep study spanning about 2 decades. And there are other sites as well that are doing similar studies. There is also a coalition for sleep study. And combined, they have about like 100,000 to 200,000 different data points from different people spanning multiple decades. But these days, people are also using these wearable devices such as Apple Watches, Fitbits, which also tracks your sleep, with the caveat that these data are a little more noisier than the structured sleep clinic data. And I'll talk more about the structured sleep clinic data in just a bit. Okay, so I probably don't need to motivate this a lot. We all know the promise of foundation model. Over the past few years, 3-4 years, let me.
I have a question from the audience.
Yeah, can this?
Address sleep disorder problem. Can this
Yeah,
be?
I'll talk about this in just a bit. The short answer is it really depends on what kind of fine-tuning data you have and how you adapt this model. But this model could, in theory, be used to fine-tune on various sleep disorders and be used to basically predict those sleep disorders and things like that. Yep. Okay. So quick refresher of foundation model. Usually these models are fairly large, trained on unstructured data or in a self-supervised fashion. You normally don't have labels for this large pre-training corpus, and you train it using self-supervision. Then you can adapt this to a bunch of downstream tasks. For example, here, if you are training the model using text, images, speech, then you can adapt it to things like image captioning, question answering, and things like that. So this is for the general domain. For the sleep domain, it may look something like this, where you have data coming from ECG, EEGs, respiratories, your EHR, electronic health record data, also your imaging data, which could be used to train a foundation model. And then it could be adapted to tasks like sleep staging, respiratory events, patient matching, and data imputation. Okay, so why should you care about this? We built the first foundation model for sleep. We have some really promising results on sleep staging and apnea detection. And by the way, apnea is, I guess, could be considered one of the sleep disorder among others. And we also have some promising future direction for predicting like cardiovascular, neurodegenerative diseases, and beyond that as well. And there's also a really exciting potential extension for this work to wearable devices. We haven't started working on it, but it's something that I'm really interested in doing in near future. Perfect. All right, I'll take a pause here and take any questions if you have any. Okay, no questions. Okay, so let's go over what the data looks like.
I have a question about
Yes.
the data actually. This data is in public domain.
No, this is not, and I'll actually talk about that right next to it. Yeah.
Okay.
Yeah.
Got it.
This data set is not, but you can find a lot of sleep data actually in public domain.
Thank you.
Yep. Okay, and I'll talk more about it. Okay, so the data set we used for this project came from Stanford. It's about a decade worth of data, 15,000 individual patient data. And this is roughly amounts to 15 terabytes. These are like really large files. Each file is about like 1 gigabytes. And 15K included pre-training, training, testing, and validation set as well. Normally, these files are stored in this file format called EDF. And this is like a snapshot of the file. This is about a 30-second snapshot of the file. You can imagine normally how it goes is you go to a sleep clinic. They hook you up with a bunch of electrodes all around your body. And you would sleep as a normal that you sleep every night. And all these electrodes are simultaneously collecting signals from your body. So for example, you have things like EEG. You can see these FP1, FC, M2 channels. They're all your EEGs that are collecting data from your brain. So they lay around your head. You also have things like EKG, which are collecting data from your heart. nasal pressure, oral thermometer, snore. These are collecting data from your mouth region and collecting data from your lungs, signals from your lungs. These files normally have a associated events file, which may look something like this on the right. So this is like the whole entire 8 hours of person sleeping. You can see there is like different stages of sleep. You have wake, stage 1, stage 2, stage 4, REM sleep. And you also have things like obstructive apneas, which are the, like sometimes when you sleep, you may have some moments where your breathing temporarily stops. Those are like the apnea events that you have. And sleep stages are basically you go through different cycles of sleep as you are sleeping through the night, and that's just representing that.
So one quick question, Rahul. So this annotation data, did you collect it from the automated annotation file, or did you collect somebody manually looked at the data, annotated it?
Yeah, so actually all these annotation come from like the sleep expert. So
No,
they,
because you understand, right? Like there are two different ways usually we collect the annotation data. One is actually collected automatically by the sleep annotation machine, which is generally automated annotation. And then if sometimes if you want to get like more detailed annotation, somebody like sleep expert, they manually look at those files and do the annotation.
yeah. So my understanding is this has been done manually.
So
As far
all
as,
on all the 15K patient, or do you have a subset?
yes, as far as I know, I think they are done manually. But I can double check and get back.
Okay.
Yeah.
I think we have another question.
Why are there so many wake points? Yeah, maybe this is just this specific patient had a lot of instances where the person was waking up in the middle of the night, but you're right. This is probably just this one specific instance that I had.
So this is a very good question actually. So this is particularly related to the OSA. So there are records that if a patient has a many OSA event like obstructive sleep apnea, then the patient will have many more chance of having the wake event.
Yeah. Yes.
Because if they don't wake, they actually die. You understand, right? They can have a chance of like dead.
Yes. Yeah. I don't know the clinical details about that, but that sounds right. Yeah.
We have another question, I think. So is the snore and audio data?
Yeah. It is collecting the audios. Yeah, as far as I know.
Thank you.
Okay.
I think the data is more heterogeneous because literally most of the data is collected from Stanford. So like the concerns that were raised about the sleep apnea and having more of the wake listing in the proportion of the data, it's going to skew the training of the model, because I'm looking at it from a perspective. Even myself, I'm a clinician, also I'm a medical doctor. Looking at this data, it's not really representing the entire demography. So it makes it look as if sleep apnea or all these conditions are not prevalent. Meanwhile, that's not the true story. So I think it would be possible to give more data outside of Stanford. It will really help in your work. Thank you.
I agree. Yeah, that's a very good point.
That's a very good point, and I was actually going to talk about that in the limitation of the work. You're exactly right. If you are looking at just one site, and even just if you are looking at this sleep study from any sites, normally the person who goes to sleep clinic are the people who already have these pre-existing conditions. So that is exactly right, and we are in the process of building like a next version of this model, where we extend the dataset site and also validate this on multiple sites to make sure that we can generalize across different sites. I'll take this result as almost like a preliminary result or proof of concept work. Was done mostly on one site, but we do have an external validation result that I'll show in a bit. Does that answer the question?
Yeah, sure.
Okay, perfect. Good question.
So, Rahul, how this annotation looks like? Can you give one example how the annotation looks like?
Yeah, it's literally, so you can think like you have timestamp, right? And each timestamp would have a label as wake, stage 1, stage 2, things like that.
stage one starting and is it a bioannotation? Bioencoding?
It is a, sorry, what did you say?
Bioencoding, BIO, bioencoding.
I see. I'm not sure what that means, but literally you can think of it like a CSV file with two columns. One column has the exact timestamp. Let's say hour 7 to 7:30, I don't know, like 30 seconds past that time, and then you have the event for that on the
Okay,
other.
got it. Thank you.
Yep. Okay. So good questions, and you can keep the question coming as I'm talking. I'll try to finish one section and then just take all the questions after that. I'll pause there, and then if you have any question, you can put it in the chat. I'll answer after finishing a section. Okay, so let's go over the modeling approach we used. So I'll give a quick refresher of the backbone of our framework that we used, and then I'll talk about the specific approach we used. So we use something called clip style contrastive learning, which is very common in the image domain, image and text domain. So the intuition here is you may have data from representing similar thing from different modalities. Here, the modality could be a text and an image. So for example, you can take a look at this figure. You have the paper, the Aussie pup, and you have the image of the Aussie pup. So this could be considered like representing something similar in two different domains. So intuitively, when we train the model, we want to bring the representation of these embeddings from the same object as close as possible in the latent vector space. And you also want to make sure that we are pushing away the dissimilar embeddings. Let's say our text describing a cat and an image of a dog. So they are two different things, right? We want to push the representation of the embeddings of these dissimilar objects as far as possible. So if you are considering a batch, you can see a batch of text and a batch of image. They are all paired one-on-one. So you can project them into an embedding vector through some encoder. So you have text encoder and image encoder here, and each one of these T1, T2, T3 are embedding vectors. So think of like a 512 dimension vector for each one of these T1, T2, T3. And if you look at the diagonal element now, they're all one-on-one paired with their corresponding text and image. So during the training time, you try to maximize the similarity of this diagonal element or try to bring the embeddings as close as possible while minimizing everything else that is not in the diagonal, which are the dissimilar objects in two different modalities. Okay. So that's like the standard clip style contrastive learning algorithm. So I'll now talk about how we use that framework for our purpose. So just like I was talking about two different modality, like the paired modality, the text of a dog and a image of a dog. For us, the positive pairs, so by the way, those are called positive pairs, and all the not associated modalities, for example, text of a cat and an image of a dog, those are called negative pairs in the language of the contrastive learning. So here, the positive pairs for us are the temporally aligned signal data from different modalities. And I'll explain what that means here. So think of like, so BAS is basically brain activity signal. ECG is your heart signals, and respiratory data are coming from your lungs. And left to right, we are going from start of the sleep to the end of the sleep. So first of all, we chunk these into, say, like 30-second clips. You can see like this dotted box. These are like 30 seconds, approximately 30 seconds. Then if you look at the 30-second clip from one modality, and if you go down a different modality, they are all temporally aligned, meaning they are all being collected at the same time from the same patient, but with different parts of the body. So our intuition is they must be sharing some information across the sleep, across different organs in the body, which we can then leverage to train the contrastive learning algorithm. Just like we were training, like basically pairing the image of a dog and a text of a dog, we consider this as the positive pairs, and any other randomly selected clip. So for example, this clip against any other clip from this modality from different patients could be negative clips for training the model. So I'll stop here since this may require some clarification.
I have a question over here. So, can you hear me?
Yes,
Yeah.
I can hear you.
Yeah. So, say for example, I'm just curious. So, the length of the BAS is similar to the total length of this BAS signal is going to be similar, the same as the total length of the ECG signal.
Yeah,
Like if it's 10
they all,
minutes, it's also 10 minutes. Like sorry. Yeah.
yes. So usually they are in the orders of like multiple hours, like standard average sleep about like 8 to 10 hours, something like that.
Okay.
But since they are all being created simultaneously, they are all of the same length.
And also another question, like say for example, it's an 8-hour thing because yeah, that's a standard sleep, proposed sleep cycle or somebody like that's like people expect that you should sleep for 8 hours and so through that entire 8 hours, you're like dividing this entire 8-hour long like signal into 30 seconds. That's
Yes,
what
that's right.
why 30 seconds? Like, is it because like could you not do like 10 minutes or 5 minutes or something a little bit longer, like say for example, 15, 20 minutes?
Yeah, that's a good question. You could do that. In fact, the model that we are training now allows you for more granular even.
Okay.
But in this study, we mostly focus on like sleep apneas and sleep staging events. Normally, sleep stagings are scored in a 30-second clip or 30-second epoch, they call it. So
Okay.
that was one of the main reasons why we picked 30-second, but you don't have to. You can also change the window.
Okay.
But if you don't have overlapping window, there could be a chance that you can divide the same event into two different blocks, right?
You could divide the same.
So imagine,
that's right.
yeah,
That's right. But we don't care about the events yet when
because then if you can pair with the hard negatives, you can have the same event in the hard negatives
you can have the same event hard negative.
because you are considering that the same temporal things are aligning, so they are positive and everything else is
Yeah.
negative, right?
Yeah, so that's a good question. Since the search pool is so large, we are randomly selecting from all the clips in all the patient. I think it's reasonable to assume that they will probably be from something very different. But also, we don't really care about the stages per se in this stage of pre-training. It's
But even
almost,
OSA, why not? Like the OSA can also be divided into multiple minutes, not only 30 seconds.
yeah, you could. I guess my point was we don't necessarily care about the events just yet.
Even if you don't consider event, but still the contrastive learning, that is the whole idea that hard negatives are different from the positive examples, right? From the
Yeah.
anchor and the positives.
Yes. Your intuition is right. Ideally, we want to select as hard negative as possible.
Right.
But to make it like generalizable across different tasks and things like that, we just like selected a random clip from the entire pool of clip. And it worked reasonably well, or actually pretty well. So we just stick with that.
So why you didn't choose the sliding? Because if you have overlapping window, it could at least maybe better represent the boundaries, right?
Yeah, we actually did have a sliding window experiment as well, and empirically it was about the same
Okay.
As the just having like a separate disjoint clips, and we just stick with that for that reason. Yeah.
Okay. Because I was curious because since you mentioned that you have the annotation, probably then better to use the annotation to define your hard negative and positives, right? Rather than going it in a random selection.
Yeah. So yeah, that's right. But we wanted to be stricter to the usual way of doing this, which is basically we didn't want to provide a lot of input from the downstream task during the pre-training stage, because normally the assumption is during the pre-training stage, you just assume that you don't have the labels. The only thing that I think we took as input from the fine-tuning stage into the pre-training stage is the size of the clip, which is 30 seconds. But we try to not use any other information during the pre-training stage.
Okay.
But I agree with you. I think it will help if we could also select like really hard negatives, like a really different clips for sure.
Oh, one question I have is that are events very common across like the whole time span of like hours of sleep, or is it possible that your 30-second clips are they just fall into kind of the background signal type thing where there's nothing happening, nothing is of interest, and that stage is just similar across all patients?
Yeah, so that's a very valid point as well, especially in the beginning of the sleep and the end of the sleep. There is a lot of noise when they are setting up, probably when they are setting up these devices, and when the person is not fully asleep, there is like a lot of noise. So I could see how this could be even further improved if we account for those cases, and maybe like the person before you were saying, if we select those hard negatives very intentionally, this could definitely be improved. But like I mentioned, we try to make it as generalizable as possible while doing minimal signal processing, and still show some promising results. Having said that, we are working on the version 2 of this model where we are much more careful about the things that we just talked about.
No, thank you.
Yeah, very valid point though.
We have one more question from the audience. So would it be fair to treat signals from the same stage but different time points as negative pairs?
From the same stage but different time points. I guess theoretically that could happen if you are picking randomly from all the pools of the patient. Yeah, I do. So with my minimal knowledge of the sleep stages and from the clinical side, I do. It may be the case that even within the same sleep stages, but across the different patients, it could be slightly different. But I wouldn't know without knowing the clinical details of that. But that is a possibility that could happen.
Okay, thank you.
Okay. So let me move on now. Okay, so positive and negative pairs. Hopefully those are clear now. So after that point, it was just a matter of doing something very similar that the clip style contrastive learning would do, which is you have encoders, separate encoders for each modality. You generate the representations, and then you do the contrastive learning. So I showed you the contrastive learning for 2 modalities before, which is very simple. You do the you use the cross entropy loss to minimize the loss. You use the cross entropy loss and minimize the cross entropy loss. But when you have more than 2 modalities, the most standard way of doing it is pairwise contrastive learning, where you are taking each pair submodality together at a time. You are calculating the cross entropy loss, and then you are adding the losses, and then you are backpropping and optimizing and things like that. So that's the standard way of doing it, as I show in the top. So this embedding versus this embedding, this versus this, this versus this. We also propose something called leave one out contrastive learning, which is in spirit very similar. But what we do is, so let's say we have 3 modalities. We leave one modality out. We aggregate or average the embedding of the remaining modality. So we have 2 remaining modality. And then we do the same kind of contrastive learning framework that we did. And we do it for individually for each modality. So if you do the math, you have like n times n minus 1 by 2 pairs of losses for the pairwise, but you have n losses for the leave one out. And more so than the compute efficiency, this helped us a lot in the performance boosting. And we think that this is mostly because leave one out contrastive learning is a slightly harder task than the pairwise contrastive learning. Now, we really haven't delved like deep into the theoretical understanding of this exact framework, but empirically, I would show you in a bit. Almost across all of our tasks, leave one out is performing way better than the standard pairwise contrastive learning. Okay, I'll stop there as well, just to make sure the framework is clear.
Can you explain a bit more in detail about the leave one out? Like, how does that mathematically work? Which 2 embeddings do you contrastively learn?
Yeah. Okay. Sounds good. So I'll take a simple example of the 3 modalities for now. So you see, you have 1, 2, and 3 modality. So let's say, so eventually it'll give you three different losses for each one of the modality. So for the first loss, what we do is we have the embedding from, let's say, BAS encoders. You keep that out. You aggregate the embedding from the ECG and respiratory signals. You literally just average them together, and then you do the
Okay.
click-style contrastive learning, and you do it.
So you just average the two embeddings?
Yes. So for the
Okay.
first loss, so that gives you the loss for BAS, and you do the same thing now for the ECG. You take it out, aggregate the other two embeddings, calculate the cross entropy loss, and for the third one as well. So if you had n number of modality, you'd have n number of losses.
Got it. Thank you.
So is all your modality are represented to 2D image, or they have different encoders? Like something is like 1D encoder, something ECG is like 2D.
Yeah. So these are all these are n number. So we have n number of channels, and each one of these channels are 1D signals. So you can, I guess, kind of sort of consider them as 2D. The encoder itself takes the 2D signal itself.
So represented as image, not as 1D signal.
Yeah, I'm not sure if we can say represented as image, but because they are.
I just wanted to understand, like, if they are represented as image or they are represented as a 1D signal. If they are represented as a 1D signal, then probably you need a 1D convolutions or something like that.
So we are using 1D convolutions, but so the convolution is occurring in this fashion. So you are convolving across the temporal dimension, but also the spatial dimension. So I guess you could say that sort of like the image, but yeah, I wasn't thinking about it that way. Yeah, but we have the code open source, so maybe if you're curious, you can take a look and see if the implementation is similar.
Okay, because my main concern is that the ECG encoder, BSC encoder, respiratory encoder, since they are actually dealing with like different types of very heterogeneous data, and when you just calculate the average, probably you would be fading out some of the effects on some of the encoder. For example, I don't know, like ECG signals, they are sometimes like so minimal values compared to the respiratory signals, so probably you can just null them out if you just average them with ECG encoder.
I see what you mean. Yeah, that's a valid concern. Actually, we did have one evaluation on the paper where we tried to study like the number of modality we average out, and it is definitely the case that some modality is helping way more.
Right, and it makes sense, right? Because their scale would be very different.
Oh, no. So just to make sure I understand. So the aggregation is being done in the embedding space, not on
even if you do it on the embedding space. For example, ECG, sometimes they are like, for example, the BSC channel, sometimes they don't have any signal at all. They are just kind of like looks like noise, right?
So in that case, the embedding will just not contain much information about that specific modality, but
right. So if when you average out with, for example, respiratory, probably you will not have any information from the BS.
But that's what we want, though, right? Because in that case, the BS in fact doesn't have much information, which is fine. No.
But if you don't have the information, then why to do the average out? You can just do literally leave one out that don't include that modality at all. Why to do the averaging then?
But we don't know. So what you're proposing is we probably need to handle specifically for all the cases. Here it's
the signals, like the signal should be handled differently as you're doing here, like the encoder wise. And before you average out, you either have to normalize everything to the same space or do something on that part so that when you average out, they have at least some effect.
So that's what we do. That's why I was telling you it's not being done on the signal space, because if we do in the signal space, your concern is very valid. On the embedding space, once they're all normalized.
But they're normalized with their own encoder, right? You're not normalized with their like a common encoder.
All of the branch is different, so they are being
so they are normalized with their own encoder, so they can average out in their own space, not in a different space.
Yeah, I'm not sure if I understand. Maybe.
No worries. Yeah, you can continue.
Yeah. Okay. Cool. Yeah, but feel free to reach out to me afterwards. I'm happy to discuss more about this. Okay. So I'll quickly walk you through some of the results we have, and maybe take questions after this section again. Let me quickly time check. Okay, perfect. So the first sort of like a sanity check evaluation we did was if we can retrieve clip from different modalities. So basically what I mean is, given the clip from the brain activity signals, can we retrieve the corresponding clip from, let's say, ECG? And this will kind of show that the contrastive learning is working, because this was exactly how the model was also trained or pre-trained. So you can see on the left, given this 30-second clip, can we retrieve the clip from the different modality? So normally these are measured using this matrix called rank and recall. So imagine you have the entire pool of clips, and you have a clip from one modality. So you basically do like a dot product with all the clips. You rank them or you sort them out, and you see where the gold clip is ranked in that list. And ideally we'd want it to be ranked or occurring in the top, let's say top 10 or something like that. So recall at 10 is looking at the top 10. Median rank is basically looking at how often it comes in the front. So for example, if the median is 1, 50% of the time it is happening, the gold clip is occurring in the first rank. So here the lower number is better, here the higher number is better, and this is just like a very quick sanity check to make sure the contrastive learning is working. Okay, so again, a few more sanity checks before we go into the actual results. We did like A's and gender classification as well. So we basically grouped the A's into different groups, and we calculated the metrics for AURC and AUPRC. So leave one out is our framework that we proposed. Pairwise is the standard one that I talked about. And supervised CNN is basically, it has the same encoder as we use for the pre-training time. We just remove we just like change the output head into a supervised learning head. So you have n number of classes, and you directly go from data to the classes. Without going into too much detail, the general story here is the pre-training is helping. As you can see, the pre-training performance on average is better than the supervised CNN. And especially the leave one out is also performing significantly better than the standard pairwise approach.
So sorry, how in the supervised CNN you combine all the features, all the embeddings?
So the supervised CNN is literally taking all the channels as the input.
No, I understand, but for example, you have ECG, you have BAS. How you are combining those embeddings together, the supervised CNN?
So you have the EEGs, right?
You are only doing this with EEG, the age classification, or you are also including the other modalities too?
Yeah. So let me quickly explain. So you have the band of EEG data, which goes through the encoder, and then you get the representation. You have the ECGs, you have the respiratory signals. All of them goes through the encoder, grabs the signal. And then we basically pass it through one more layer to combine the embeddings, and then basically have the classification head as like let's say the age group that we have. So it is seeing all the signals that the pre-trained model might see.
Sorry, probably I missed it again. So I don't understand really. Like you have the CNN encoders for each of the modalities, and you are predicting the class, right?
Yes,
Are
that's
you
right.
predicting the class from each of the modalities separately, or you are combining these modalities?
No, all of the data is combined together. Yeah.
So that's what I'm asking, right? How you are combining after you pass it to the CNN encoder?
So something that you can do is something like you can do like literally average pooling.
So you are doing average pooling, or?
Yeah, in this case, I think it is average pooling, yes. But we also
why
have.
are you not? Because if you want to do a fair comparison with the contrastive learning with all the modality on the supervised CNN, you should do either like average out, or you should do at least the concatenation, right? So the model has chance to look at all the features simultaneously.
Yeah. So so we did both. The one that so it is seeing all the channels as it is with the concatenation that you talked about, and also the average pooling we did. So both of the results should be on the paper, and it performs very similar. I only showed you one of the result just to convey the story, but it is seeing all the channels of the data, not just one versus the other.
Okay.
All the channels from all the modalities. Does that make sense?
Yeah, I'm not sure because since you just mentioned here supervised channel, so it was not really clear like what architecture for supervised channel.
So yeah, let me try to be a little clear. So
No, I understood. Yeah, you can continue. Yeah.
Yeah, you can literally remove this contrastive learning and replace this with the classification head. Yeah, but we can follow up offline if you're still unclear, and I can also show you the code if you want. Yeah. Okay. So same thing for gender classification. We have AURC, AUPRC. I'll quickly walk through this result now, and maybe take questions. But the story is similar. We are performing better than the supervised CNN, and our approach is performing better than the standard approach. The class here is just male and female. Okay, so for the sleep stages, the story is again very similar. The leave one out is performing way better, and even within the group as well, our model is performing better than the standard approach and the supervised CNN. The supervised CNN is in fact seeing all the channels, just to make sure we are on the same page. They are seeing all the channels that the pre-trained model is seeing, and the training data is exactly the same for the pre-training model and the supervised CNN.
I have a question over here. Do you see these distinct, I think, 4 or 5 stages in all the data that you have, or there are some where you don't see some of the instances in a particular class or something, like a particular stage? Or does all the data have all these 5 instances, like 5 stages?
Yeah. So generally they do. At least I haven't seen a patient that did not have some stage, but I don't know if clinically that's possible. Yeah.
Okay.
So you take the Stanford data and divide it into pre-training, training, validation, and testing because you don't have an external validation at least up to this point, right?
Not until this slide, yes.
Right. So you divide the data into four part, or you are using the pre-training data also in your training?
4 parts, like you said.
Okay.
Okay.
And Rahul, you've, I think, discussed like channels already, but just out of curiosity, how much temporal information you need to classify a stage? Like 30-second clip is generally enough? Like these numbers are coming from just 30-second stages?
Yeah, usually, although the standard might be different now, but I followed this the sleep guideline, which may be a little old, but it did say that 30-second is the standard. There is some interest now we're getting from other folks that are interested in doing even more granular sleep staging. So like 10 seconds, 5 seconds. On the next model, it'll be more granular than 30 seconds.
And similar architecture for both like gender and age prediction, just the 30-second, the numbers that you were showing, they were pretty amazing. So that's just coming from like a 30-second clip.
Yeah, gender and age are more like a patient level metric. We kind of pool the log props to make sure that we have a patient level prediction.
Oh, okay. That makes sense. Thank you very much.
Sorry, okay. How is the model able to differentiate between being awake and the rapid eye movement stage of sleep? Both of them have similar brain waves. Have you been able to look at it to be able to find what are, because when you look at the signals, they are literally almost the same, except the other one happens at the later stage of sleep, just before waking up. So how is the model? Because I'm expecting that if we create a confusion matrix, it will help us to look at the wake and the REM sleep, because both of them there should be false negative and false positive interchangeably at this place to tell us that actually our data is a little bit more accurate. If our data cannot, because these two actually have similar brainwaves. So, and confusion matrix will give us a clearer picture to know that our model is actually struggling with that. If not, it will just be memorizing the labels. Thank you.
I see. Yeah, I didn't actually know that the wake and REM, like you said, have similar brain waves. I wish I had my clinical collaborator with me today, but yeah, I wouldn't be able to tell you any more than that without knowing exactly what the clinical details are. But from the model
They have
perspective,
similar brainwaves.
okay, I'll trust you on that if you have clinical experience then there. But
I
from
have
the model,
experience in there.
sorry, what was that?
I have clinical experience in there.
Yep, there you go. I trust you. What I was trying to say was I probably can't and shouldn't comment on that. From the modeling perspective, at least, there are more metrics on the appendix of the paper that you can take a look to see how these classes are being differentiated. My assumption was the wake and REM was quite different, but I was wrong on that, like you said. From the model perspective, it's usually really hard to exactly understand what the model is doing. All of this is like a black box. But hopefully in near future we can provide more interpretation to why the model is doing specific things. Perhaps looking at some specific segment of the signals and things like that.
Okay.
Yeah, that's a good point. Okay, so lastly, we
Any
have
plan to bring up a confusion matrix in the next evaluation? Is there any attempt to add a confusion matrix? Like I said, that's where we're going to see that confusion actually taking place. The model trying to differentiate between the wake and the rapid eye movement phase of sleep. Because I feel that going forward, I think if we're going to make, or if you're going to make a robust foundation model is something that's going to be vast to capture. The data points are actually going to increase beyond the brain waves and respiratory data and the ECG. Simple things like pulse oximeter will be very, very important. And then even getting the musculoskeletal activity generally, because one of the key difference, if you are looking at the REM and the wake cycle, the other one, the person is asleep, so there will be less muscular activity as compared to when the person is fully awake. Mentally, a lot of distractions, eye movement, musculoskeletal activities a little bit high. So they can bring some, salient differences. So meaning that there will be need to take more data point, considering beyond just taking the brain waves, taking the respiratory data and the ECG, So there are other parameters. Of course, even the way I'm not sure if those data were collected in the clinic or they were given to the patients to go home with them when they were actually sleeping, because that will also help us to classify things like insomnia, to know, okay, what was the duration of each sleep cycle for each individual, each row of the data. How long? Some sleep 3 hours, 4 hours, 5 hours. Those factors will need to be kept in check. Issue of medication. So there are other data points that are actually missing here that will actually enrich and help create a very, very good classifier.
Yeah, I think I got most of it. Just to make sure I understand you right and take it to the team. So you are saying there are other data points than just the EEG, ECGs, and respiratory signals we have that could be included for making the better classifiers. Do you mean specifically sleep staging apnea or some other events? And what are those data points, I guess?
Yeah, other data points include current medication.
Oh, I see.
Yes, if they are on medication. Yes.
Oh, I see.
There are other medical conditions.
Yes. You actually predicted what we are doing right now, which is, in fact, we did pair a lot of the Stanford data with their electronic health record data. And we are in the process of including those information that you just mentioned. Like specifically, we have information about their comorbidities, like their history, their medical history, and also the medications that they took. So you actually were point like a very good point in there.
Of course, even coffee can also be important rollouts. So they are going to make the information quite rich, because for someone that is taking caffeine-related beverages, obviously it will affect their sleep pattern. And over time, it's actually going to numb the neurons that they no longer become sensitive at that level of stimulation to either sleep induction or being awake. So such things will actually really go a long way to make a robust foundation model, since we are calling it a foundation model, not just baseline stuff. Yeah. So we will see later.
Yeah, in the interest of time, we can take these questions offline. Maybe we'll have the speaker details as well as the entire thing will be online on YouTube, so we can let the speaker continue with the talk. Yeah. So
I'm almost done with my slides as well. So I'll quickly wrap up. Out of interest for people who wanted to know about the external validation, we did validate the model on a publicly available external dataset that was in Stanford. And the story was again similar in terms of the metrics. So out of interest of time, I'll encourage you to go check the paper. We have details about exactly what site was used and things like that. The code is also open source. So if you're interested in exactly the encoders, what the supervised CNN look like and things like that, it's also all there. You can always like ping me with the questions about the code if you're interested. Okay, so I'll end with this slide. Quickly summarize what we did and some of the future work that we are looking at. So, like I said, we built the foundation model for sleep analysis. This was more of a proof of concept work to show that it works. And we used two different kinds of contrastive learning, pairwise, and our main approach was leave one out, which performed better than the other approaches. We also evaluated on different demographic attribute classification, sleep stages, and apnea detection. For future, some of the things that we are working on at the moment is extending it to more sites. We also want to make it channel agnostic in the sense that you can have different number of channels, EEG channels at different sites, EKG channels at different sites. We want to be able to account for that as well. And this was also brought up already. There are other clinically relevant tasks that we want to consider. There are medication information that we want to consider. So all of that is also being done at the moment. And with that, I'll end there, and I'll take any last minute question you may have before I leave. Yeah.
thank you so much, Rahul. We would like, before we open up the floor for more questions, we would like the audience to give him a virtual round of applause for such an awesome and an engaging talk. It was a really nice work.
Thank you. I appreciate it.
Yeah. So yeah.
Yeah,
So we have one question. Is the data publicly available?
Yeah, so it's really hard to get this scale of data publicly available this soon, but our hope is hopefully in future, at least some of it will be publicly available, but not at the moment. There are other publicly available sleep data. For example, the one that we externally validated on, it is publicly available. So yeah, if you are interested in looking at this data, this should be easily available.
Okay. Do we have any more other questions?
I have a quick question on the averaging the embeddings. Yeah, great presentation, Rahul. This is amazing. So what I was intuitively struggling with the averaging of the embedding. So let's say you had fruits, right? So I have an embedding for apple, I have an embedding for orange, and maybe the embedding for pear is somewhere close to those two embeddings, right? When you average these ECG embedding and the other BAS embedding, like the meaning, it feels like I'm just struggling intuitively to understand what's happening when you are doing an average of the embeddings. Is there some other way to like maybe fruits and cars, right? So I'm like, if I am, so something like that. Yeah.
Yeah, no, I think that's a very valid point. Intuitively, to understand averaging is something that you just said, which is normally in the word vector space.
Yeah.
You may have embedding for like let's say queen, king, and when you subtract that, you get like a embedding for something else.
Right.
Intuitively, what might be happening is you have an embedding from brain activity, from respiratory, and they are all temporally aligned. So you may have some embedding that has like a part of information from brain activity signal and respiratory, like a mix of information. But I don't know if you can exactly pinpoint as easily like a man minus a queen equals to women, something like that, that easily. Although we could probably project this embedding into like a two-dimensional image through some UMAP and things like that, and explore what is actually happening. We didn't do that, but that could be a possibility to check what is happening.
Okay.
But Rahul, I have to go back to the previous question again, since Mahul asked that, because that is only possible if these embeddings are generated on the same space. Because you can do the vector operation when they belong to the same space, right? Otherwise, you have to align them in the same space.
So,
but what you are doing is actually you are doing the pairwise averaging or whatever it is on the embedding that are generated by different models. So basically, they are in different space.
So usually how it works is when you're training all these models jointly. So if you follow the, let's say, vision language model space, a lot of the times you have this layer called projection layer, right? Added in
Yeah, but
between.
you have previously you have a cross attention. That's why you are aligning them and then you are doing the projection.
Well, you actually can just have like a linear layer going in between these models.
Yeah, that's I completely agree. But for your case, when you are doing the averaging out based on the pairwise averaging out, as you mentioned in CNN, you are just averaging all the modality, but you don't have any linear layer.
So I see you mean like maybe you should have like a linear layer in between these three.
Yeah, exactly.
I see
and
what
then
you
you do the projection and put all them in the same space before you do any kind of vector operation, right?
I see. That's a good point. We did have linear layer individually across all the modality, but maybe having like a one shared projection layer.
Because otherwise the CNN validation is not also meaningful, because you understand, right? Because the CNN, how it will learn the concatenation of the feature when they are generating from a defined space.
Yeah, I see your point. Yeah, let me think about it a bit more. Maybe I'll run experiments to see if that actually helps. My hope was, even without that, since we have linear layer on each one of these models separately, that kind of brings the embedding to the embedding space. And when you train all these models jointly, like through the pre-training process, it should be all brought into the same embedding space. But that may not be the case, like you mentioned. So let me do some experiment on that, and then see what happens. Thank you for the feedback.
Okay, so I guess we can end our session over here. Again, I would invite people to kind of extend another virtual round of applause to Rahul. Thank you so much, Rahul, for the awesome talk. And with this, we can end our presentation.
Cool. All right. Have a good one.
Thank you.